by Sandy Irani. My name is Sampath Kannan. I'm the incoming Associate Director at the Simons. For the one or two of you who don't know what the Simons does, it is the preeminent center for research in theoretical computer science, bringing together people from around the world. But it has an outward-looking perspective as well, as the quantum program and the ECC program this semester demonstrate. We build bridges with physics and math and other fields as well. So that's the Simons Institute. A brief word about the Richard M. Karp lecture series, which was founded about 5 years ago, I think. Richard Karp is a giant in the field of theoretical computer science. That's underselling him. He probably is considered the founder of theoretical computer science in some sense, and in many of its sub-areas as well. Sandy was actually one of Richard Karp's students, working on one of the areas where where Karp was a pioneer on online algorithms for her dissertation. But over the years, she's moved on to working on other areas. So my task of introducing Sandy has at least a couple of ironies, and I'll point out the first one is that 2 months ago, she was introducing me. So while I think that Sandy needs no introduction, it probably is definitely safe to say she needs less of an introduction than I do, but I am introducing her anyway. Well, Sandy, after her time working on online algorithms, has migrated to quantum almost entirely over the last 15 years or so. And she has done some amazing work on proving the hardness of one-dimensional Hamiltonians. They're proving that one-dimensional Hamiltonians are QMA hard. The other irony is that I have to do the introduction before her talk, because after her talk, I would understand what I'm saying. But I will just pretend that I understand for now. So the other thing I want to say is that I took over from Sandy as associate director, where, I mean, she was very beloved here because she was so warm and gracious as an associate director, never let the pressure of the job show, and left me almost no loose ends to worry about. She completely documented what the job involved, took care of most of the problems. So she made my life very easy succeeding her. So I thank you for that as well, Sandy. And without further ado, let's have you.
So thank you for inviting me to speak, and it's really an honor to speak in this lecture series that's named after my advisor, Dick Karp, and his work figures prominently into the topic as well. So it's especially nice for that reason. So I took my marching orders seriously to try and make this as broad as possible. So my apologies if I'm going over your bread and butter, your basic material in excruciating detail. I'll try and sort of put in something here for everybody, though. So we're going to start with a really sort of basic setup where most of us are familiar with. We have a set of Boolean variables. And with that comes a set of constraints. And each constraint is just a little function, little Boolean function on a small number of the variables. So I've shown here a function on x3, x5, and x7, and then we can sort of explicitly describe it. So we have m of these. And the goal is to find some global assignment to all the variables that minimizes the total cost. And the cost is just the value of the sum of these functions on the assignment that we're given. So because in computer science, we tend to like to work with decision problems, yes, no questions. We can imagine that we're given some threshold and we want to know, is there an assignment whose total cost is at most t? When I refer to Boolean satisfiability, I'm talking about satisfying all the constraints. So the sum should be 0. Oftentimes with SAT, we think of the convention as satisfying this constraint, it being evaluating to 1, but it doesn't matter. It's just a convention here. So, all right. So as promised, we're going to actually look at a quantum version of this. So instead of variables, we'll have particles. Instead of these little classical functions, we'll have terms describing the energy interactions between small groups of the particles. And the goal is to find a quantum state that minimizes the overall energy. So we will unpack this a little bit over the next 15, 20 minutes just to sort of understand to come to a sort of a more formal definition of that problem. So just a quick primer to quantum information, classical state on n bits. It's just a string on n bits. as a stepping stone on our way to quantum, we can imagine classical information with uncertainty, which is described by a probability distribution over the 2 to the n strings. And the L1 norm of this vector would be sum to 1. And then when we move to quantum, a state is still represented by a vector, but now these entries can be complex. Okay? So sometimes our intuition about probability distributions carries over nicely into the quantum setting, and sometimes not so much. So the fact that these are complex, and in particular negative, is part of what gives quantum science and information its complexity. So what do these complex numbers mean? If I were to actually measure this state, so first of all, we think of the state as sort of being partially simultaneously in all these different states. And if we were to measure the state, the likelihood that we have a particular string as the outcome would be the magnitude squared. So it's a sensible probability. And we want these probabilities to sum to 1, so that just means that the L2 norm of this vector is 1. Okay. And in quantum computing, we need to apply operations that preserve this L1 norm, which means that any operation that we apply to a quantum state has to be what we call unitary. So it has to preserve this L2 norm. Okay, so basic postulate of quantum mechanics is that any observable entity, momentum, energy, what have you, corresponds to a Hermitian operator, just meaning that the eigenvalues are real. So where does this operator come from? Well, also, part of the postulates of quantum mechanics is that if I measure an n-dimensional system, I can't get, if I say measure the energy or the momentum, I can't get any old output. I'm going to get one of n possibilities if it's an n-dimensional system. After I do my measurement, I have to be in a state that's consistent with that measurement. And so each of these states indicates that the state is a state that's consistent with, say, a measurement of, if I measure the energy, the output of lambda 0 or lambda 1. So what's this operator? Well, it's just the unique operator whose eigenvalues are lambda 0 through lambda n minus 1 and have eigenvectors, which are these resulting states. And the nice thing about this formalism is that once I can sort of describe this operator and put it in its matrix form, now measurement can be described by matrix multiplication. If I have some generic quantum state described by a vector, I have some measurement, some quantity I'm measuring, the expected outcome is now just this simple matrix multiplication. So it sort of gives us a means to evaluate these expected outcomes. So the Hamiltonian plays an important role in physics because it describes the evolution of our quantum system. You don't really have to understand this, but we will be focusing on Hamiltonians as the energy, the operator that will occupy most of what I'll talk about today. So if you feel like you haven't met a Hamiltonian before, chances are you have. Here's a hydrogen atom, which is a little quantum system. And the state of the system is just the position of the electron relative to the proton. So I can describe it here in polar coordinates. It has a Hamiltonian, which is the kinetic energy of the electron and the potential energy between the proton and the electron. And if you measure the energy of a hydrogen atom, you can get only one of, you can't get any, it's not a continuous output. It's going to be a discrete set of possible outputs, and here are the eigenvalues associated with each possible measurement that you can get. So now what's different here is that the state is sort of a continuous variable, this location. We will be mostly concerned with systems that have discrete bases. So we're looking at quantum systems composed of d-dimensional particles. Most of the time I'll just use d equals 2 to call them qubits. So each of these can be up or down. And the dimension of the system is going to be a superposition of all 2 to the n possibilities. So it has 2 to the n. So if a state in this system is generally described by a vector of length 2 to the n. And the Hamiltonian is an operator, which is our energy operator, is a 2 to the n by 2 to the n matrix. And so what we're going to be concerned about today is taking this Hamiltonian and evaluating its lowest eigenvalue. So, and the ground state is the eigenvector associated with this lowest eigenvalue. So, and in particular, we're concerned with what we call local Hamiltonians. So this is going to be the sum of terms, and each term only sort of operates on or describes the energy interaction of a small set of these particles. So if I have a term that describes the energy between these three, say, electron spins or qubits, it's going to be described by an 8 by 8 matrix. Okay, and so, but of course, it's sitting in this larger system with n particles. So it's really a 2 to the n by 2 to the n matrix. And the way we get from the 8 by 8 matrix to the larger matrix is just tensoring with the identity. And that just looks like this. So it's a lot of little copies of this. Okay, so Hamiltonians, we have a really nice, succinct representation of what we call a local Hamiltonian. It's a sum of terms, each of which acts on a small set of particles. So there are at most n to the k terms, if k is the number of particles that each term acts on. And each is described by a small matrix. If my particles have dimension d, there are d to the 2k entries in my matrix. Okay, so nice, succinct. Now the Hamiltonian itself is a huge object. Okay, and so finding the smallest eigenvector, I mean, we can do eigenvector calculations and eigenvalue calculations, but the matrix itself is huge and too large to write out explicitly. Okay. So where do Hamiltonians come from? You can imagine engineering a Hamiltonian. So possible, you could create a Hamiltonian whose ground state encodes a solution to, say, a computational problem that you're interested in solving. And so that's the idea behind adiabatic computation, where we have some starting Hamiltonian, some final Hamiltonian. The starting one is easy to prepare, say the ground state is just all zeros. And we slowly change our system so that we end up in this final state. And the idea is that if we measure this final ground state, then we'll get the answer to some problem that we're trying to solve. Say it's a combinatorial problem, you could encode that as the ground state of a Hamiltonian. And now the speed with which I can travel this path and remain in the ground state is related to the spectral gap, so that the gap between the smallest eigenvalue and the next highest up. And this is actually a serious proposal for a model for a quantum computer. The company D-Wave is based on adiabatic computation. As a serious model of computation, as a serious implementation, it's a little problematic because we can't do error correction. But it's proposed as a possible model. And we know that, for example, that it's equivalent to our more familiar circuit-based model. So anything that we can compute with the circuit-based model can, at least in theory, be computed with this model. More often, though, Hamiltonians come from nature. And so we use them to describe natural phenomenon. They arise in condensed matter physics and material science. So one might want to understand the properties of materials and at low temperatures, and also in chemistry as well. So this is considered sort of a possible target application for quantum computers, is to sort of be able to simulate chemical reactions. And chemical reactions tend to follow a low energy path, so it's the lowest energy state that we're mostly interested in calculating. So a lot of effort of numerical chemistry is spent on finding ground states and computing low energy configurations. All right, just to make sure that you don't think I made this up, I'm going to give you sort of a concrete example picked from the numerical condensed matter literature. The reason I picked this one is that Steve White is my colleague at UC Irvine, so he was kind enough to explain his paper to me. And this is a particularly interesting one because they were looking at a particular sort of phase of matter called spin liquids. Okay, so what are they doing here? But this is sort of a typical example of what one might do in numerical condensed matter physics. And what the computation might look like. So Steve, by the way, has developed an algorithm called DMRG, which is one of the most successful classical heuristics for finding ground states and computing their properties. And he used that in this paper. So what's going on here? We have this very beautiful lattice structure. And on all the vertices, there's a spin. And on each neighboring pair of spins, we're applying this little matrix. And this is the Heisenberg antiferromagnet. So you'll notice here that we have negative values on the 0, 1, 1, 0 entries. Okay, so that means where low energy is good. So it's favoring anti-aligned spins. But we also have cycles of length 3. So it's going to be a frustrated system. So we're not going to be able to satisfy all of the constraints. So in particular, what they were looking at was they were trying to understand the structure of this ground state. Is it a valence bond crystal? So in other words, is it like a periodic pattern of entangled particles where the entanglement entirely resides within these, for example, pairs? Or is the structure what's called a spin liquid, which isn't a completely understood phase of matter, but the idea is that it's a completely disordered system. So if you measure it, you don't notice any broken symmetry like you would in this case here. And spin liquids are of particular interest. Sometimes for some systems, the higher level, the low-lying states, but just above the ground state, exhibit important physical properties and are best described as like sort of quasi-particles with sort of different physics than what you would see elsewhere. So they were interested in looking at this question. And one of the quotes from this paper is that a key problem in searching for spin liquids in 2D models is that there are no exact or nearly exact analytical or computational methods to solve infinite 2D quantum lattices. And in fact, finite ones too. So 2D seems to be kind of a sweet spot where interesting physics happens at low temperatures, but it's sort of beyond our ability in terms of what classical computers can do. Okay, so Kitaev came along and, there's this huge enterprise in numerical condensed matter physics to understand ground states and to apply numerical methods to understand their properties. And Kitaev came along and phrased this as a computational problem in a way that we as computer scientists can now look at and study through the lens of complexity. So we tend to like decision problems, so that's the way he sort of phrased this. So the input is, as we've sort of talked about, is a set of Hermitian positive semi-definite matrices, and it just means that the norm of each one of these is between 0 and 1, and each one operates on a most k qubits. Qdits is what it should say of dimension d. So we have a bunch of particles, finite dimension, and a sum of terms. So it has a nice succinct representation in terms of the number of particles in the system. And along with the input comes two numbers, a and b, but they're separated by 1 over a polynomial, where n is the number of particles in the system. And we want to know, it's a decision problem, it's actually a promise problem. We want to know, is the smallest eigenvalue of this Hamiltonian at most A or at least B? Now, the promise gap here is the gap between B and A, and this is a critical piece here because we're calculating a real number. So precision has to be taken into account. And so we're basically saying we're trying to calculate this number to within a precision of 1 over a polynomial. And it is a promise problem because if I happen to give you a Hamiltonian whose true lowest eigenvalue lies between these two values, all bets are off, and you're not required to actually answer correctly. Okay, this is a special case of constraint satisfaction. Okay, so if it happens that all of these H terms are diagonal, then the Hamiltonian is classical, and in particular, I have here a little Boolean function on 3 qubits. So I can express Boolean satisfiability or classical constraint satisfaction in this framework of the local Hamiltonians. Okay? So any theory that we have for hardness for the classical side will also apply to the quantum side. Okay, any questions? Yes?
Yeah, What is the dimension of the qubit? Is the number of qubits in one function?
So a single qubit is dimension 2 because it's going to be a superposition over 0 and 1. And so I can specify it by length 2 vector whose L2 norm is 1. Now, when I go to n qubits, there are 2 to the n possibilities. So the dimension of that vector would be 2 to the n because I have to tell you the amplitude for each one of those possibilities. Good, thank you. All right, so a little primer on complexity classes. So the class NP is essentially the class of problems for which we can verify solutions easily. So think Boolean satisfiability. If I give you a Boolean formula and I give you an assignment, ones and zeros to all the variables that actually satisfies all the constraints, it's not too hard to check it. Polynomial time, you can easily check it. Now, finding a solution might be a very difficult task. So that generally describes the problems in NP in which, in the case that the answer is yes, there is a certificate that you can verify. And if the answer is no, no matter what certificate I give you as a verifier, you won't be convinced that the answer is yes. So more formally, for a problem instance X, the answer is yes. If my verifier, algorithm A, if there's a string that I give to A and it accepts on input X and Y. So X is the instance, think of X as the Boolean formula, Y as the assignment. And it's a no instance for every witness. If for every witness, A will reject XY. Okay, so this is sort of, and now we turn to a quantum version of this, which we call quantum Merlin-Arthur. And you think of a omniscient Merlin trying to convince a limited Arthur that the answer is yes. And now we've moved a couple differences here. First of all, the verifier is now a quantum algorithm. The witness is a quantum state. And because quantum computation by its nature is probabilistic, it accepts and rejects with high probability, but there's some probability of error on either side. Okay. So why did it was Kitaev who actually named this class, and it's actually named after this intermediate class, which is classical. But now this in the Merlin-Arthur game, the verifier is randomized and accepts or rejects with some probability. So this is quantum Merlin-Arthur is actually a quantum version of Merlin-Arthur, not really NP. Okay. So witnesses always have to be bounded in polynomial size by the size of the input. And we have a natural inclusion here. So in each case, going from NP to MA, MA to QMA, we're generalizing what this verifier can do. So Kitaev proved that this local Hamiltonian problem that we just formally defined as QMA hard, I'm just going to spend a tiny bit of time stepping through the NP counterpart because we're going to generalize that to the quantum setting. So to show that Boolean satisfiability is the hardest problem in the class NP, meaning that if we had a solution to this problem, we can solve anything in NP. We have what's called a reduction. So we take a generic input of our generic problem, and we translate that into a Boolean formula so that if the Boolean formula is satisfiable, the answer to X is yes. Okay. The only thing we know about a generic problem in NP is that it has a verifier. So that's what we have to use. So basically what we're doing is we're taking this computation of the verifier and encoding it in this Boolean formula. X, the input is hard-coded into the Boolean formula. Y is the free variables. So we're saying there's a string that causes the verifier to accept over here if and only if there's a string that satisfies this Boolean formula. And the famous Cook-Levin tableau sort of is the mechanism by which this is done. And you can think of this, every variable occupying a square in this tableau. Time is going up here. So every line is a state of my computation. So time 0 here, the finish line is here. And basically what this instance of Boolean satisfiability does is it uses local constraints to ensure that this is a valid computation. And this can be done locally. So these local constraints are covering the entire grid, and they ensure that if all of the constraints are satisfied, then yes, this is a valid computation. We have constraints that check that the output is yes. We have constraints that encode the input. And so basically, this is the formula that comes from this grid is satisfiable if and only if there's a yes computation. So now we're moving into the quantum world, and we want to do the same thing. Okay, so we start with a generic problem in QMA, and we want to encode this into a local Hamiltonian problem. And we want it to have the property that this quantum verifier accepts, there's a state which causes the quantum verifier to accept if and only if there's a low energy state in the Hamiltonian. Now, it's tempting to kind of use the same formula here into the grid and to have like a qubit at every square of this grid, but that doesn't work because in the simplest case, imagine that you have an identity operation going from one step to another. We actually can't check identity by local checks in the quantum world, okay? So this basic formula is not going to work. So what Kitaev did is he encoded the progress or the steps of the computation in superposition. So I have a quantum clock register that advances from 1 to time t. And at each step, the computation register reflects the state of the computation at each step. And he builds a Hamiltonian that enforces the fact that the low energy state corresponds to an invalid accepting computation. Now, just to sort of give you like a cartoon idea of why this would be a local Hamiltonian, you want a constraint that says for every state of the form here, and I'm here at time 5, it's a unary clock, I have 5 ones in a row. If there's a state of this kind, then there has to be a state of equal amplitude of this kind, where the clock has been advanced and the gate has been applied. And you can do that with a 5 local constraint. It advances the clock and applies the gate all in one shot. Okay, back to classical CSP. At the time when Cook and Levin proved their famous theorem, it wasn't phrased in this language of witnesses. It was a theorem about non-deterministic Turing machines, and very much, it was an important theorem, but very much within the realm of complexity theory. And then it was really Dick Karp who came along and said, actually, this applies to all these problems from operation research that we've been trying to solve. So this is sort of, you know, Dick's concerns were much more pragmatic. This is like literally about the trains running on time. So, and since then, the number of NP-complete problems have just proliferated. In every field, there's some type of optimization problem that ends up being NP-hard. Okay, so what about QMA-complete problems? The landscape isn't quite as crowded. There are a few other QMA problems besides local Hamiltonian, but local Hamiltonian is basically the one we all talk about. So when we talk about coping with hardness and managing to solve these problems, the fact that most of the problems that we're concerned with are some form of local Hamiltonian sort of points us in a certain direction. So we look for symmetry or structure or special cases that we can use to sort of constrain the problem and potentially design better algorithms. So in that case, the constraints are somewhat different because the motivation is somewhat different here. So we tend to look at constraints that are sort of embedded in space in some way, 2-dimensional or 3-dimensional space. And we also are interested in translationally invariant, so meaning that in many physical systems, the constraints between neighboring particles are exactly the same. Okay, so Kitaev's construction was sort of non-physical, didn't represent sort of what physicists are often interested in for various reasons. First of all, it's not translation invariant, and it's not geometrically local. So it applies to, you know, we got this clock register and this computation register, and it's applying terms to qubits on both sides. So since that time, there have been a number of improvements. The local Hamiltonian problem remains complete QMA hard, even under sort of more physical constraints. So 2 local qubits on a 2D grid, and also on a one-dimensional chain. This one was a little bit surprising because, for 2 reasons. Partly because classical heuristics are actually very successful in 1D. So there was some hope that this would actually be easier. And also the classical variant is in polynomial time. So, okay. And the idea in these sort of geometric local ones, instead of having a clock register and a computation register, each little particle encodes part of each. So they're not qubits always, but or each little collection can sort of encode part of the clock and part of the computation. So one of the things that's sort of interesting in the quantum setting that we don't have at all in the classical setting is that there's this intermediate class QCMA. So QMA has a quantum witness and a quantum verifier. QCMA, we keep the quantum verifier, but now the witness is classical, okay? We don't look at the other way around, because if you gave a quantum state to a classical verifier, it just would be very confused. So that wouldn't work very well. So we look at this particular combination. So originally, I think it was Haranov and Nave who coined the term QCMA. And in their original paper, they actually thought that these 2 classes might be equal. So we definitely have this inclusions, because QCMA is a special class of QMA. The current thinking is now is that they're not the same, that they're quite different. We don't really have a hope of proving that, because a separation here would imply a separation between polynomial time and p-space. And as surprising as it may sound to people outside of theory, we are not able to prove that there's a problem that can be done in polynomial space that can't be done in polynomial time. So we prove other things around it. But this, to me, is still a little mysterious. So if just take for a second to think about what it means if they're really not equal. It means that these ground states of local Hamiltonians are so inaccessible to us that we can't even construct them. So for example, if every local Hamiltonian, you could at least construct the ground state with a quantum circuit, that would be a classical witness. I could hand the verifier the recipe, the classical description of a quantum circuit, and you could build the state, and then you could check. So somehow there's a new level of sort of mystery about these ground states. So NP has, the witnesses are hard to find, but if you're given one, you can verify it. If this separation is true, then they're not only hard to find, but you can't even construct them. So, but yet there's a verifier who knows it when it sees it. So there's still a little bit of a mystery around that. So as I said, so there are QCMA complete problems. They're not quite as natural as the local Hamiltonian. So this one is like ground state connectivity. If I have 2 ground states, can I get from one to the other by 2 qubit gates while remaining in the ground state? So it's sort of asking about the connectivity of the ground space. So what we do is we prove something else. So and oftentimes we resort to what we call oracle proofs. So an oracle is a function that we sort of magically give a model of computation access to. So if I have oracle is some family of Boolean functions, and C to the O are the problem solvable in some complexity class C that has access to the oracle O. So for example, let's look at P polynomial time Turing machines with access to a SAT oracle. Here's my polynomial time computation. At any point in time, it can just write down an instance of Boolean satisfiability and gets the answer to it right away. Okay. So we don't have the mathematical tools to prove this separation. So instead, what we do is we give each model of computation access to a very powerful oracle and say, okay, now is there a separation between the 2? So it's not quite the same. The more powerful the oracle that you give these models of computation, the weaker the result in terms of the separation. So it's, you're giving you're giving these models access to this very powerful oracle and then asking harder questions than it could ask otherwise. And then in the context of QMA, you can think of like adding like an access to the oracle as just a little gate that sits inside your quantum circuit. So I just give you these gates for free, and you can sort of place them anywhere you want. Classical functions don't always work so well in quantum circuits. As I said, they have to be unitary, so our computation has to be reversible. But there's a nice way to easily make a classical function reversible as a little gate that I can sort of embed in the circuit. And then we can also query them in superposition. So I can have some superposition in inputs and get the superposition of outputs in one step. Okay. So we know that these two classes are separate with access to a quantum oracle, which is very powerful. We don't know if they're separate with respect to a classical oracle. And there's been a lot of interesting work in between that looking at sort of hybrid versions like classical oracles with randomness, limited access to the oracles, or some types of specialized quantum oracles. There was a really nice talk at the last workshop by Angelos Pelikanos on the different oracle models. So if you're interested in this, I recommend that talk. Okay, so let's talk about search decision now. So as I said, as complexity theorists, we like to work with decision problems. They're simpler. And we justify this to ourselves by the fact that the search decision usually isn't too far off from the decision problem. Meaning that, so usually you're not just interested in knowing if a graph has a Hamiltonian cycle, you want to know what it is. Or you want to know what your satisfying assignment is to a Boolean expression. And so usually in the NP world, this isn't too much of an assumption just to restrict our attention to decision problems, because basically if you can solve the decision problem, you can usually solve the search problem. And sort of more formally, if I have the function version, this is just the function version of P that outputs a string. If it has access to a SAT oracle that can tell me the yes/no answers to my question, then I can build the satisfying expression. So how would that work? You'd basically just sort of fill in the variables one at a time, asking your oracle at each point, is this expression satisfiable? You'd start with the initial expression. You'd try plugging in a 1 for the first variable. If it said no, then it has to be a 0, and on you go. So you could, through n oracle calls to the decision oracle, you could slowly build up, bit by bit, the solution to the problem. Can we do the same thing in the quantum world? So first of all to notice is that this local Hamiltonian problem, as I've defined it, it's inspired by quantum computation. It's defined by quantum computation, but it's a classical function. It takes to input a classical description, it outputs a classical bit, okay? And we can imagine an oracle to the decision problem. So I feed in a description of a Hamiltonian, my thresholds A and B, and I get out the bit, yes, there's a low energy state, okay? Now, can I use a gate of this type to actually construct the witness? That would be sort of the analog to the search to decision question in the quantum world. So can I take in a description of Hamiltonian, access to as many copies of this fancy gate that I want, and can I actually output the state itself? Okay, another question we can't answer, but we can do it with there's an oracle separation between the two. And how the oracle figures in here is a little sort of technical to go through. But just to sort of give you an idea of why this might suggest that it's not possible is that all these other classes have search to decision reductions relative to any oracle. So I can slap on any oracle to both and the search to decision reduction works. So it suggests that there's something different here in the quantum world instead of constructing these states. I think I'm going to, in the interest of time, I'm not going to go through the more technical part of general state synthesis. But we did look at the question of, so let's say an oracle for Hamiltonian, local Hamiltonian isn't sufficient enough, let's say I have a more powerful oracle. Can I build the state in that case? And it turns out, yes. So this, if I have access just to one call of an oracle in the class PP, which is probabilistic polynomial time, then you can build the ground state of a local Hamiltonian with high probability. And PP is a very powerful class. So it's like the decision version of counting. So a polynomial time algorithm with access to a PP oracle will contain the entire polynomial part. So we're resorting to a more powerful class, but we're only using one oracle. We also looked at general state synthesis, not just how complex is it to construct quantum states under certain conditions, and how, if there's a classical function that gives you access, that you have access to, how many queries does it take? And it turns out that any arbitrary state can be constructed by just one or two queries. And in a follow-up paper by Greg Rosenthal, he showed that just one query to a classical oracle is sufficient to construct any state, any quantum state. And before I move on to the next topic, let me just say that there's like a nice new theory developing around sort of the complexity of where the objects themselves that you're outputting are quantum. So most of our complexity theory has to do with classical inputs and classical outputs, but that doesn't necessarily make sense in the quantum world, where you may be asking to what's the complexity of constructing a particular state. So the state synthesis question says, given an implicit description of the quantum state, how complicated is it to construct that? And similarly for the unitary, given an implicit description of a quantum operation, how hard is it to perform that operation on an arbitrary input state? And there's a very nice talk by Tony Metker at the last QIP, sort of introducing this area. So I recommend that if you're interested in hearing more about that. Go past this. And let's talk about approximation. So one of the big crowning achievements of complexity theory since the theory of NP-completeness was the proof of the PCP theorem. PCP stands for probabilistically checkable proofs. That's hard to say. So what's the idea? So I'm going to describe it in this framework, and then we'll talk about how it relates to approximation. So in the normal scenario, with a verifier and prover, the verifier tells the prover its instance of SAT. The prover sends back an entire string, and the verifier checks. In the probabilistic setting, you do what you would do when you have a big stack of homework to grade. You spot check, okay? So instead of just handing over the entire assignment, the PCP prover provides a longer proof, but still polynomial size. And the verifier just needs to check some random locations. So it uses some randomness to pick a constant number of locations, and it can check those and be reasonably confident that it's satisfiable if all the checks check out. Okay, so what does this have to do with approximation? Well, there's a natural sort of approximation version of this that says that the following problem is NP hard. So this is like a Boolean SAT with a promise gap, okay? So the following promise problem, I'm going to give you a Boolean formula, and I'm going to guarantee you either that it's entirely satisfiable, or every assignment has at least a constant fraction of unsatisfied constraints. So you can see why this might be probabilistically checkable. I don't have to check them all. If I pick a random constraint with reasonably high probability, I'm going to catch you lying if it's not a true satisfying assignment. So how hard is the corresponding problem in the quantum setting? So what this would correspond to saying is, how hard is it to approximate the ground energy? So here's our lowest eigenvalue. This is our target. QMA-completeness says that it's hard to approximate within a 1 over poly gap. Since local Hamiltonian is a special case of NP hard problems. We know that it's NP hard to approximate to within an additive linear factor. And the conjecture, the quantum PCP conjecture conjectures that it's actually hard to approximate. It's QMA complete to approximate the energy. Okay, this would presumably be a slightly smaller constant in some way. And what are the challenges in sort of extending the classical proof? It has to do with copying bits. So here's an example of a step in the classical proof of the PCP conjecture, where you have a variable that's participating in a lot of constraints and you want to reduce the degree. So one way to do that is just to make copies of the variables, add constraints that the value is consistent with on those copies, and then you can sort of distribute the constraints among those 3 copies. Well, that doesn't work in the quantum world because of the no cloning theorem. So the no cloning theorem says that you cannot make wholesale copies, independent copies of quantum information. So there's no unitary operation that takes a generic psi qubit and makes an independent copy of it. And that would be at least following the proof verbatim be a necessary step. And I should add that we do know that the quantum PCP conjecture won't hold for these geometric type Hamiltonians, because there's a sort of a straightforward approximation that's better than a constant factor. So basically, here's a 2D grid. If I chop up this grid into square root of log n by square root of log n squares, there's log n qubits sitting in there. I can brute force solve each little square independently, and the error is going to be proportional to the boundary. So that automatically gives me a better than constant approximation ratio. So hard Hamiltonians are going to be by their nature non-geometric. How much time do I have? 5 minutes? Okay. Recently, there was a sort of a breakthrough in our progress towards the quantum PCP theorem done by folks in the audience, and sort of came out of work at the Simons Institute. And it's a weaker statement because it proves something that quantum PCP would imply. So it would be a necessary thing to have in order if the quantum PCP theorem is true. And it says that there exist Hamiltonian systems such that every low energy state requires above constant circuit depth. So what does this have to do with quantum PCP? Well, the thing to notice here is that if I have a state that I can construct with a constant depth circuit, first of all, that's a certificate, a classical description of the state. And moreover, I can do kind of whatever I want with that state. I can use it to measure energy. And it's sort of a light cone argument. If I'm looking at a local term, the number of qubits that participate in that, or the number of input bits, is at most constant if it's a constant depth circuit. So I can sort of brute force estimate the energy of this individual term. And since the energy is just a sum of these terms, I can sort of brute force calculate. So if a state is the product of a constant depth circuit, I can calculate its energy efficiently. And so if it's true that if the NLTS statement is false, in other words, if every local Hamiltonian has a low energy state that's easily described by a constant depth circuit, then then it has to be the case that the problem of approximating ground energies is an NP, because that's a classical description. I can give you the classical description and you can check it. So either an NP is equal to QMA, which we don't believe is true, or the quantum PCP conjecture is false. All right, so there's still a ways to go, and I would say that quantum PCP is one of the biggest outstanding open questions in the field. I don't really have time to go through the dichotomy theorems, but let me just sort of briefly sort of give an overview, because it kind of leads into sort of what I think of as sort of outstanding open questions. So Schaeffer's dichotomy theorem was a classical result from a while ago that classified NP Boolean functions in terms of whether you could create NP-hard instances with them. And it gave a complete characterization. So if you have a set, it's either, if your constraints have those forms, that's either NP or NP-hard. It was a little surprising because if P is not equal to NP, there are intermediate classes, which is why it's called a dichotomy theorem. So it's either NP or NP-hard. There's a similar result in the quantum world. So it's a characterization of all 2-qubit Hamiltonian terms, or according to, that tell you whether Hamiltonians built up of those terms are QMA-hard or an NP. And it's a complete characterization. So the rules of the game are as follows. I give you your set of allowed Hamiltonian terms. You can take any term in that set and apply it to any set of qubits of your choice. And you can scale it by a coefficient. Okay, so it's pretty generous in terms of adding the scaling factor. But what results is a complete characterization of Hamiltonian terms in terms of their complexity, given the ability to sort of apply them anywhere and scale them anywhere. Noticeably, BQP is sort of missing from this picture. So either we kind of constrain it so that it becomes easy for a classical computer, or it's NP-hard or QMA-hard. I think we believe that quantum computers will be useful in finding ground states, but we don't quite know exactly how to harness that power yet. So non-physical aspects are the fact that it's a general interaction graph. You can have positive and negative coefficients. Both of those are sort of non-physical. A lot of those were addressed, but this sort of coefficients varying by a magnitude of polynomial seems to be inherent to the techniques of sort of building these gadgets and perturbation theory. So one could ask, is that really a necessary component of hardness here? So I'm just going to take as sort of a closing picture a particular example. This is an XY model, sort of studied in physics. We know that applying this term to every edge in a triangular grid, if I'm allowed to tune the coefficients, it's QMA-hard. We also know that it's QMA-hard if I apply it to a general graph with 1 or 0 coefficients. Okay, but the graph itself is quite complicated. And there's a little caveat here in that we're sort of confining ourselves to a particular sector of the space with a fixed Hamming weight. Okay. We know, and so you could ask, what about just this term on a simple grid? What can we do with that? We know that in general, there are hard 2-particle terms. So translationally invariance and no coefficients is enough to make everything easy, because we know that there exist Hamiltonian terms that are in general hard. But these are somewhat complicated constructions, not a nice little qubit Hamiltonian like this one. So this is still sitting in the middle. What about this model or others like it? Bose-Hubbard, there are many examples. On a regular 2D lattice with just uniform coefficients, we don't really know the complexity of this. And I don't know of a lot of candidate heuristics for it either. So presumably a quantum computer would help with this, but this is sort of the meat and potatoes of condensed matter physics, and I don't think we know yet how to harness a quantum computer to solve these problems. What quantum computers do well is they simulate dynamics well, and they can do guided state preparation well. So if I give you a state that has a high overlap with the ground state, it can increase that overlap. But finding that initial state seems to be a difficult problem. So recent progress. People are working on near-term quantum computers to see if you can heuristically construct ground states. We look at special cases like where there's a spectral gap or commuting case. I mentioned this particular paper because it's one of the few examples where there's a quantum algorithm and not known polynomial time classical algorithms. So there aren't a lot of these. And recently there's sort of a very exciting results on thermalization and constructing Gibbs states, which looks like it might be a new algorithmic paradigm which can be leveraged for this, but we still don't really understand very well how and when and why it works. So there's still work to do. So thank you. drop out his office hours at 4:30. I had a hard day. Yes.
So when you mentioned it's a promise, the Hamiltonian problem is a promise problem. So if I have a Hamiltonian and I don't know anything about it, I don't know if it's gapped or not, then can I learn something about it?
Well, I mean, I think this is sort of a problem even in sort of the experimental literature. So you have some Hamiltonian system that you're studying, and you can use your numerical techniques to show that there is a state of at most a certain energy, but you don't necessarily know, is there something better out there? So I think that's sort of an inherent problem. This problem is sort of a construct that we use to sort of study from the complexity view. But at the end of the day, the problem that you have is, given the Hamiltonian, what's the minimum, what's the smallest eigenvalue of this Hamiltonian? And I don't think we fully understand the complexity of that problem either. We do understand it in the classical world. So we know that, for example, if I give you a Boolean formula and say, what's the maximum number of constraints that you can satisfy? That's a class, that's an oracle class. That's P to the NP. But we don't have a similar tight kind of characterization of that in the quantum world.
Oh, that's cool.
Yeah.
So imagine if you have a powerful enough oracle, you could make QCMA with respect to that oracle equal to QMA with respect to that oracle. Is that true? And if so, how powerful an oracle do you need to make that?
Huge.
So you talked about inequality, but what about equality?
I'm going to crowdsource that question. Yeah, P-space, yeah. So they all sit inside P-space. So
I see.
yeah, so yeah.
Okay, clear? Okay, those it's in P-space.
Then I think you can do anything, probably. You know?
Even
QMA.
Even QMA. Oh, yeah.
Oh,
There you go.
okay.
That makes sense.
Okay.
Yeah.
Sorry, QMA.
Is that clear?
Because for NP is not the case, right? Because you can solve co-QMA as well.
Yeah, NP, the NP is sigma 2 or yeah.
Oh,
Yeah. So it's not.
yeah.
Yeah, but P-space with a P-space is P-space. That's
Yeah.
But do you need to go all the way to P-space
Yeah.
or?
I don't.
I don't know.
Any other questions?
It's a little French, but have you seen any balanced ternary satisfiability as well as Boolean satisfiability?
I'm sorry, I didn't.
If you have -1, 0, and 1, then have 4 satisfiability and a 3 setting. Have you seen such directions for Boolean satisfiability?
And you're taking products and sums of these things? I don't know the complexity of that. With negative ones. And then you can have cancellations and sort of, that looks a little bit more quantum now, doesn't it? So I don't know, actually, yeah. Yes?
So I have a question. So you are saying like quantum cannot solve for 2D grid because we have an algorithm with approximation of 1 over root log n.
Uh-huh.
But 1 over root log n, is that the best we can do? Or-
Oh, I don't know. Yeah, I mean, I don't think we have a hardness of approximation beyond the +1 over poly. So we're that far away. So that would still be interesting progress, is to show that, approximating to within, even 1 over log is hard. Yeah. So there's a big gap between the gaps that we can.
I have a comment.
Yeah.
So someone told me like the precision which chemistry people care about is 1 over n. So if you come to QMA on the component program with precision 1 over n, is in BPP, then you solve a big problem. Because so in complexity, we prove QMA-hardness for 1 over poly precision.
Yeah.
It seems people care about, in practice, people care about 1 over n precision.
You want last question over there?
Yes, so you mentioned earlier like this Adiabatic model where you can somehow go from like
The Adiabatic, yeah.
the solutions. So how does this, sits together with the fact that the local Hamiltonians are QMA hard? Is it that it works just for special cases?
So I'm sitting already in the ground state of a Hamiltonian, and I'm going to sort of the ground state of another Hamiltonian. Oh, so you're saying if that in the QMA case, I don't know that the gap is bounded. So if I'm going to the ground state of a generic local Hamiltonian, I can't guarantee that I'm not going to pass through some intermediate Hamiltonian with an exponentially small gap. So then it doesn't work. But if I know that my destination Hamiltonian happens to be just the output of a quantum circuit, then we can actually prove a polynomial gap for that path. So it depends on where that, whether you can prove a lower bound for the spectral gap, not just at the beginning and the end, but this funny mix of Hamiltonians in between.
Same thing.
Right.